Friends, in this video we are detailedly study about the different types of three-phase drives. Such drives are called as the half converter drive and full converter drive. So let's begin. Friends, in this video we are detailedly study about the different types of three-phase drives. Such drives are called as the half converter and fully converter drive. So friends, before we going to start this bit, we want to understand what are the different types of DC drives that we had already studied in concern with the DC drive. So friends, there are different classifications of your DC drive. So the DC drives are classified into basically four types. So the first type of the DC drive can be classified as the single phase drives. So in single phase drives, friends, we are using the single phase supply. So such type of drives are called as a rectifier fed drive. Okay. So in concern with the single phase drive, friends, there are different two types of drives are there. First one is called as single phase half control drive, and second type of drive is called as single phase fully controlled drive. So friends, I think in the previous video that we had already discussed about what do you mean by the half control drive and what do you mean by the fully controlled drive. So friends, in this video now we are moving towards the next classifications of your DC drive, and this is the classifications of DC drive basically in concern with what that is the three-phase drives. So what do you mean by the friends three-phase drive? So friends, in three-phase drive that we are using a three-phase supply for your converter. So such kind of drives are called as a three-phase drive. So friends, as we know that what do you mean by drive? The system employed for motion control, that is we called it as drive. And if we are employing the electrical motors for your motion control technique, then definitely we are called it as the electrical drive. So friends, when we are using the three-phase supply to control that particular motion of your motor, then definitely it is called as three-phase electrical drive. So in concern with the three-phase electrical drive, such drives are called as the rectifier fed, means we are using the rectifier circuit to feeding that particular three-phase drives. Okay, so the first type in the three-phase drives are called as the three-phase fully controlled drives. So in fully controlled drives, we are controlling, that is full wave, or we can control these the different types of drives in a fully manner that we can discuss in this particular bit. So friends, this will be the first type, and second type, which is called as the three-phase half control drive. So what do you mean by the three-phase half control drive? So in three-phase half control drive, friends, we are using basically again the three-phase supply, but the control of your operation, it is a half. So the construction of such kind of three-phase drives are totally different, that we will discuss later. Okay, so this will be the second classification of your DC drive. So friends, after that we can move towards the next classification of your DC drive, and such classification of DC drive is called as the dual converter fed drive. So in dual converter fed drive, we are using the two converters. So these converters are rectifier fed basically. And the last classifications of your DC drive, this is called as DC to DC converter drives, which is called as the chopper fed drive. So friends, in this video we are basically only concentrating on the three-phase drive, but before we going to start discuss that particular three-phase drive, you have to know the basic concept, what are the different classifications of the DC drive, and these three-phase DC drives are belonging to the different classifications of the DC drives. Okay, so friends, let's we will start to discuss in detail about the three-phase drives. So friends, first thing, the three-phase drives are again that will be classified by the two types. This is the three-phase drives, that is called as a half converter, and the second one which is called as a fully converter. So friends, this will be the basically three-phase fully converter drive, that is the three-phase fully converter drive, that will be the first classification, and the second classification is called as three-phase half control drive. So what will be the difference in between that particular, friends? So the difference in between half converter and fully converter is that we are converting the value of your output voltage by means of the different waveforms. Such waveforms are half control and full control. So in industry, friends, we are preferring obviously the three-phase fully controlled rectifier in most of the time in application, instead of the three-phase half control drives, because the ripples are large in concern with the three-phase half control drives that we will discuss later. Okay, so this is the classification of your half phase drive. So first one is three phase fully and three phase halfly. So friends, in three phase, again we are using the three phase supply, that will be in three phase supply we are using in half control. But friends, what is the difference in between three phase fully controlled and three phase halfly controlled? In three phase fully controlled, we are using six number of thyristors, that is a symbol of your six number of thyristors. But in three phase fully controlled or three phase half control rectifier, we are using three number of thyristors and three numbers of diodes. Okay, so this will be the basic fundamental difference in between three phase fully controlled drives and three phase half control drives. Okay, so friends, let's start to discuss about what are the different concepts. So friends, obviously such type of three phase fully controlled rectifier fed DC drive, basically why it is used, because up to the rating of below 15 kilowatt, that we are preferring a single phase drives. But while the rating of your motor will be greater than 15 kilowatt to the several thousand of the kilowatt, that time we are preferring such kind of three phase converter circuit. Why we are preferring this? Because the power rating of three phase converter rating is more. So that's why if you want to apply the load that is more than the 15 kilowatt, that time we are preferring a three phase converter drives. Okay, so why we are using this particular three phase converter drives for the rating of that is 15 kilowatt and basically above 15 kilowatt or up to the several thousand, that is several thousand means 5,000 or 6,000 kilowatt. So for that particular rating we are preferring such kind of rectifier circuit. Okay, so friends, why we are using this? So basically the ripple in a voltage waveform is less in a three phase converter circuit, because in the single phase converter circuit there are different types of ripples are there. Ripples are more, so ripples which will be present in the three phase circuit, that will be the very less. So this will be the less ripples in a three phase converter circuit. So that's why we are preferring a three phase converter circuit instead of the single phase. So obviously due to the presence of the less ripple, the current is smoother and mostly continuous. So in concern with the three phase converter circuit, the current value is smoother and that will be the continuous conduction. So this will be the another thing in which we are preferring three phase converter circuit instead of the single phase converter circuit. So that will be the very important point. So friends, in concern with the three phase, friends, now we can discuss about in concern with three phase half and three phase full converter circuit. Three phase half converter circuit, the DC components are more. The DC component are more in concern with the three phase half converter circuit. So in industry, most of the time while we are using a three phase converter circuit, we are preferring a three phase fully converter circuit for your application. Because why? Because the DC components are present in your half control rectifier. Okay, and the DC component in three phase fully controlled rectifier is less. So that's why in industry most of the time we are preferring that will be the three phase fully converter circuit. Okay, so let's start to discuss the first type of converter circuit, that will be called as the three phase fully controlled drives. Friends, this will be very interesting concept while designing a electrical drive with the help of three phase control drives. Okay, so friends, In concern with the three-phase fully controlled rectifier, so this fully controlled rectifier controls 6 pulse fed separately excited DC motor drive is as shown in figure. So friends, as shown in figure, we are using a three-phase fully controlled drive. So as we have know, three-phase fully controlled rectifier will using the 6 number of thyristors are there. So friends, this will be the thyristor number first. This will be the thyristor number second. This will be the thyristor number third. This will be the thyristor number 4. This will be the thyristor number 5th. This will be the thyristor number 6. So we are using the 6 pulse. That we are using the 6 pulse to that particular control drive. Then friends, this will be the separately excited motor. So friends, this will be the representation of your DC separately excited motor. So as we know that the construction of your DC separately excited motor or the representation of separately excited motor will be look like that. Sometime it will be look like that. That is motor. That will be the motor. That will be the separately excitation. Now we can replace its armature circuit. So this will be the armature circuit A1 A2 of your separately excited motor. This will be the field circuit F1 F2. So this will be the separately excitation. So friends, this armature circuit now will be represented at its basic component, and these components are called as resistance, inductance, and this motor is separately excited. That's we are giving the separately excitation voltage. This is called as E, because this motor will be represented by its fundamental components of the armature circuit, and the fundamental component of your armature circuits are resistance, inductance, and the motor is a separately excited. So that's why we are giving the separately excitation supply. This supply, that is separately excitation supply, will be called it as E. So this will be the representation of your motor, and this motor will be separately excited motor. Okay, and the output across your motor, which will be treated as an VA. So this will be the VA is called as the output voltage across your motor. Okay, so friends, in that particular circuit we are using three-phase fully controlled drive. So the name itself indicates its meaning. We are using three-phase supply. So friends, here we are using the three-phase supply. So maybe that the three-phase supply will be R, Y, B, but for your sake of understanding, now we treated that the supply is called as ABC, A, B, and C. So friends, what will happen in concern with that? Let's we can understand. So this will be the supply, that is the supply number A. This will be the supply number B. This will be the three-phase supply, basically 440 volt or 415 volt AC supply, because as we know that the rectifier is a device which will convert the alternating current supply. That is a rectifier circuit or three-phase fully controlled. That will be the rectifier control circuit, which will convert that alternating current supply into your direct current supply. So it will convert AC into DC. So that will be the pulsating DC basically. Okay, so that will be the pulsating DC. So that will be the pulsating DC. So this will be the actually value of your firing angle. So that will be the fundamental concept. So this will be the again the pi plus alpha. So depending upon that we can control the rectifier. So we are using a three-phase waveform. This will be the single phase waveform, but here, so this will be the representation of phase A, and if we are using a three-phase waveform, so this will be the A waveform. Again we are called it as B waveform. Again we called it as the C waveform. So it will be the three-phase supply, and depending upon that we can get the output waveform of such type of converter. So this three-phase supply is given to your three-phase fully controlled rectifier. So what will happen basically friends in concern with your three-phase fully controlled rectifier? First of all, we are connecting 6 number of thyristor. So this will be the symbol of the 6 number of thyristor. Basically these 6 number of thyristors are considered as the 6 pulse. So 3 are connected in upper side and 3 are connected in lower side. Okay, so friends, this is called as one leg of your circuit. This is called as one leg. So for your three-phase supply, this will be the one leg, this will be your second leg, this will be your second leg, leg number 1, this will be leg number 2, this will be leg number 3. So friends, we are using a 3 leg. Okay, so this will be the thyristor 1, this will be the 2, this will be the 3, this will be the 4, this will be the 5, and this will be the 6. So friends, in that particular circuit we are using 3 legs. So each leg contain 2 number of thyristor, that is thyristor number 1, 2, okay, for leg number first. For leg number second we are using again 2 thyristor 1, 2, and for leg number 3 we are using again the thyristor number 1, 2. So this will be the representation of 3 leg and 6 number of thyristor. So friends, let's we can understand what will be the flow of the circuit in concern with the 3-phase fully controlled rectifier. So friends, first of all we can understand this will be the value of the basically armature current we treated as the value that is called as IA. And what do you mean by IA? It is the value of armature current of your circuit. Thus it is the armature current, and VA is called as the armature voltage. Armature voltage, that is the voltage across your armature circuit. Okay, RA is the resistance of your armature, and LA is called as the inductance of your armature circuit, and E is called as the excitation voltage for your motor because it is a separately excited. Okay, excitation voltage, okay. So these are the various terms in concern with that particular diagram. Let's friend we can understand what will be the conduction state or what will be the flow of operation. So for friends, first operation, the thyristor 1 and thyristor number 2 are conducting. Okay, so basically this will be the 360 degree, means we are using the 360 conduction. So each leg for your 120 degree conduction, that is 120 and 120 degree conduction. So each will conduct for your 60 degree. So each thyristor conducting phase angle of your 60 degree. So this will be the very important concept. Means 60 60 120, 60 60 120, 60 60 120. Okay. So this will be the concept. So friends, we can start the conduction state. So this will be the first of all we can conducting. This will be the thyristor number first to the armature current, that is IA. Then this supply is going from that particular motor. Okay, so this will be the supply going to the motor, and this will be the phase, that will be the now after current IA it will be returns from the AC. This will be the, so for first operation or the first leg, the conduction of thyristor, that is T1 and T2. So the flow will be look like that. So that will be the flow of your current. Okay, that is the phase will be going to T1, then motor, then T2, then return. Okay, so that time the operation will be the AC. Okay, then the second time we can consider the operation, that is the when excitation or when we are giving the, because we are giving the simultaneously three phase supply, but for sake of understanding we have drawn a separate supply. Okay, then at that time the next pair will be conducting, this will be the T3. Okay, so this will be the T3. Again this current will be flowing from the armature circuit. This will be the resistance, this will be the inductance, this will be the separately excitation, and from that particular T3 now it will be moving from T3 to, this will be the T4. This will be T4. So this will be the BC operation. Okay, so for BC operation the thyristor number T3 and T4 are conducting state. We can understand the same operation by means of the waveform. Okay, so this will be the second case. Okay, so in which we are conducting the thyristor number T3 and T4. It will give you the output voltage across your phase, that is phase number BC. Okay, then we can understand for the third operation, when we are giving the supply to the phase C, that will be the C. That time, friends, the thyristor number 5 and 6 are operating condition. So this will be the thyristor number 5. Okay, 5 to armature current, then armature current to armature resistance, then armature inductance, then the excitation voltage E, then it will be moving from, that will be the thyristor number 6. Okay, so from this will be moving to the thyristor number 6. Okay, so for that operation we are treating, that is a thyristor number 5 and thyristor number 6 in operating condition, and we are getting the output voltage at CB. Okay, so this will be the actual operation of your DC separately excited fed 3-phase fully controlled rectifier. Okay, so we can understand the same working principle with the help of that particular waveform. So friends, let's first of all we can see what are the different things. These are the sequence of operation, sequence of thyristor. Okay, so this will be the sequence of thyristor operation. So this and this, because we are using, these are, that is 135, this is from your upper leg, and friend, this is for your lower leg. What do you mean by upper leg? What do you mean by lower leg? That we have studied. So friends, this will be the part of your for your sake of understanding, this will be for your upper leg. This is treated as an upper leg, and this is treated as an lower leg. We call it as lower leg. So friends, in upper leg we are using the thyristor, that is are the odd number of thyristor. This will be the odd number, means T1, T3 and T5. And in lower leg we are using the even number of thyristors. Such thyristors are T2, T4 and T6. Okay, so this will be the called as the upper leg, this will be the called as the lower leg. So friends, this will be the representation of your upper leg. This will be the representation of your upper leg. In which upper leg we are using the thyristor number T1, T3 and T5. Okay, and in lower leg we are using the thyristor number T2, T4 and T6. Okay, so this will be the sequence of thyristor operation. This is for your upper leg. I can mark it as yellow for your upper leg and considered as white for your lower leg. Okay, so friends, we can understand the waveform. After that we can understand the waveform. So what will be the waveform? So first of all we can understand this will be the 3-phase waveform representation, because we are simultaneously giving to the 3-phase supply to your converter circuit. So for sake of that, first of all we can understand a single wave, that will be the sinusoidal wave, that will be shown by your dotted line. For your sake of understanding, first of all you can understand, friends, this will be the very simple waveform. For your understanding, if you have got the actual concept of your waveform, so this will be the, friends, pi means it will be 180 degree, 2 pi, this will be the 360-degree waveform. So this will be the first waveform of your phase A, or we consider it as a phase R or phase A. And again from 180 degree there should be another waveform which will be shown by a dotted red line. Again this will be your waveform. So this will be continuous after 2 pi degree. So this will be the end at a 2 pi. So first waveform is look like that. So friend, as we know that from this will be the input waveform for phase number first. So friend, as we know that this is the 3-phase waveform. So as we know that this will be the pi by 3. Pi by 3 means 180 by 3. This will be the 60-degree conduction. So as we know that the phase angle of thyristor will be the 60 degree. So for sake of that, again we can draw a second waveform after the 60 degree of the first waveform. So this will be the again 60 degree. This will be the second waveform. This will be the second input waveform. Okay, so this will be the pi by 3. So from that particular, so this angle is 60 degree, again this angle is 60 degree. So from that particular pi by 3 to the 60 degree, we can draw another waveform. So this will be the another third waveform. This will be the third waveform. 1, 2, 3. This will be the very interesting concept or interesting waveforms for your understanding. So this will be the your after 60 degree, 60, then 60, here is 120, and after that there should be a 60 degree, that is 180 degree. So this will be the third waveform. So this will be the friends, this will be the output, basically the input waveform of your supply. Okay, so friends, next very important concept, the conduction of your thyristor. So friends, as we know that the thyristor number for your phase first, that is called as A to B, we called it as the conduction of your thyristor, that is T1 to T2, the conduction of your thyristor T3 to T4, then the conduction of your thyristor, that is T5 to T6, and that will be represented by its sequence of operation. That will be the first of all, that is T1 and T2, then T3 and T4, and then T5 and T6, and this operation will remain continue. Okay, so means T1 T2 T3 T4, then again this T5 and T6, then again T1 T2, again T3 T4, and again T5 T6. So look like that the operation of your thyristor is sequentially changing. So depending upon that particular operation, now we are getting very important concept, that would be the concept that we are getting the output voltage waveform. So friends, we are giving the firing angle for that particular thing, and that the firing angle which will be treated as a 30 degree, that is the triggering or the firing angle of your thyristor. This is called as alpha, and basically now we can draw this waveform for alpha is equal to 30 degree. So friends, I can erase all the things. Now we can concentrate on the alpha value is equal to 30 degree. So we are considering the motoring operation of your three-phase fully controlled rectifier in concern with the firing angle of alpha is equal to 30 degree. So this will be the value of alpha is equal to 30 degree, because friends, we know that this will be the total angle which is 60 degree, and that is the 50%, means this will be the firing angle which is called as 30 degree alpha. So friends, this will be the firing angle of alpha. So we can get the output voltage in concern with that. So this will be the actual firing angle of your alpha. So we can get the output voltage of your three-phase fully controlled rectifier. This will be the output voltage waveform, that the output waveform I can draw with the help of the red color. This will be the output voltage which will be getting across the armature of your DC separately excited motor, and this will be the armature circuit which will be treated as. So again friends, this will be the output waveform of your armature circuit. The voltage across, that is VA, is output voltage across of your armature circuit. This will be the waveform that I have drawn, that is dark waveform. So this will be the output waveform of your VA. This will be the output waveform of your VA. Friends, very important concept, and this is nothing but your pulsating DC. Means we are giving the three-phase supply, that is the phase A, phase B, and phase C, and we are getting the output voltage from that particular operation, and that the operation is now called it as a pulsating DC. So this will be the value of the pulsating DC by the operation of the angle. This will be called as the VA. This will be the actual VA output voltage. This will be the VA output voltage. VA. Okay. So the angle for the firing angle is basically alpha is equal to 30 degree. So this will be the actual firing angle value. Okay. This and this will be the firing angle value of alpha. Okay. So friends, in this way we have discussed the output voltage waveform of your VA. It will be the basically armature voltage of your separately excited motor, separately excited armature separately excited motor. Okay, and this will be the output waveform, which is very important. This is called as VA of three-phase fully controlled rectifier. So this will be in concern with your VA. Now we are moving towards the next important concept. This is called as in concern with your armature current. So friends, as we know that in a three-phase fully controlled rectifier, we have the basic concept. The current is on continuous conduction. So now I can represent current. So friends, this will be the waveform of your current. This will be your waveform of your current, and this will be the friends continuous conduction. Friends, continuous conduction means what? It will be a continuous in a operation condition. So friend, this will be the called as the armature value of current. So this will be the armature value of current of your three-phase fully controlled rectifier. So this will be the VA, and this will be the value of IA. It will be the armature value of current, and this armature value of current is continuously in a conduction state. So friends, in this way we have detailedly study about the motoring operation of a three-phase fully controlled rectifier fed converter circuit for the firing angle of a 30°. Now we can understand the basic concept of three-phase fully controlled rectifier circuit in different operating condition. Now the operating condition is changed, because as we know that friends, three-phase fully controlled rectifier will be operated in a two quadrant. That will be the quadrant number first and quadrant number 4. That will be the very basic concept while we are studying the DC drive. This will be the first quadrant, this will be the fourth quadrant. So three-phase fully controlled rectifier drive will be operated in two quadrants. First quadrant is the first quadrant, and second quadrant of operation is your fourth quadrant. So the first quadrant of operation is called as the forward motoring, and second type of operation is called as reverse braking. Okay, because we have the multi-quadrant operation of your DC drive. So this will be the three-phase fully controlled rectifier will operate in quadrant number first and quadrant number 4. So friends, previously we have studied the operation in the quadrant number first. Now we are moving towards the braking operation. So this braking operation is called as a reverse braking operation. So reverse braking operation when the firing angle is 140°. Okay, when the firing angle is 140°. So friends, this will be the representation of your firing angle, and now we can see the firing angle value is 140°. The firing angle of your, because this will be the 60, then that will be the 60, and that will be the 20. So this will be the total firing angle of your alpha is total 140°. Okay, but this operation is what? Braking operation. That's why the output waveforms are available in a fourth quadrant of operation. Okay, so this will be the three-phase fully controlled rectifiers operation in a braking mode. So friends, this will be again, this will be the called as the sequence of operation of your thyristor. This will be the sequence of operation of your thyristor. So friends, basically this will be the sequence of your operation for a braking operation. That is, these are the called as the upper leg, and this is called as the lower leg for your operation. That will be the lower leg. So friends, in again the upper leg, we are using the thyristors. Such thyristors are conduction. This is called as T1 thyristor. T3 and T5 means the odd number of thyristors are conducting for your upper leg, and one thyristor is conducting from the upper leg and one thyristor is conducting for the lower leg for a particular operation. So in lower leg we are using the thyristor number 2nd, thyristor number 4th, and thyristor number 6 for your operation. So friends, this will be the sequence of your operation. Now we can move towards the output waveform. So friends, again the output waveform is remaining the same. So if you want to draw the output waveform in concern with that, so first of all we can understand the basic first waveform drawn. That will be the for the angle of your pi. Okay, so this will be the first input waveform. Okay, this will be the for pi. This will be for your 2 pi. So the phase displacement in between each phase is 120 degrees. So this will be the 2 pi. So from 60°, now we can draw the another waveform for your second phase. This will be the second waveform from 60°. Okay. So this will be the input waveform. So this will be the second waveform. So after this will be the 60° phase difference. This will be again 60° from this. So we can draw the third waveform from again 60 degree from here. So this will be the your 60 degree. Okay, so this will be the called as the input waveform of your three-phase fully controlled rectifier circuit for your braking operation, because in a fourth quadrant we are considering in a fourth quadrant. So friends, in that particular, now we are getting the output voltage in manner, but in a reverse direction of that particular waveform. So the output voltage, now I can show you this output voltage, only I can show you the output voltage. So the output voltage from the firing angle of, that is the firing angle of 140 degree. So friends, this will be the output voltage. Again, we have the value of VA. Okay, so this will be the value of VA, friends. This will be the value of VA for braking operation where alpha is equal to 140 degree. This will be the value of VA. This will be the value of VA. Okay, and the sequence of operation of your thyristor, that is depending upon your phase sequence. So depending upon your phase sequence, so this will be the value of the output voltage VA. Okay, so we can dark it. So we have getting the output voltage waveform. This is called as VA, that is voltage across the armature circuit of your DC separately excited motor. And the next waveform is the continuously waveform of your armature current, because we are getting the continuous conduction mode. So this will be the continuous waveform of your armature current. This will be the continuous waveform of your armature current. This is IA that we can show. So this will be the value of your armature current IA. Okay, for your three-phase fully controlled drive for a braking operation. Braking operation means in a quadrant number 4. So quadrant number 4 we are having this type of waveforms. So that's why the output waveform is looking like that. Okay, so friends, this is the explanation in concern with the braking operation, while the value of firing angle is a 140 degree. Okay, next friends, now we can start the operation by taking one of the example. So for the understanding of the example, we can take the transfer of your current from the thyristor number 5 to thyristor number 1 can be occur as long as the line voltage VAC is positive. So friends, in that particular, as we know that in concern with the 4 quadrant of operation, we are having the value of voltage and current. Again, it will be very important thing. This will be the 4 quadrant of operation. This will be the value of voltages. This will be the value of current. So both the voltage and current are positive in the first quadrant of operation. Okay, so this is called as the first quadrant of operation. But in second quadrant of operation, what will happen? The value of voltage is negative, but the value of current is what? Positive. So this will be the treated as an quadrant number 4. Okay, so the shifting of your thyristor from 5 to thyristor 1 can be occur when VAC is the sequence of your operation, where that will be the value is obviously positive. Hence, the thyristor T1 firing angle is measured from the instant that is VAC is equal to 0. Means if you want to measure the value of the firing angle from the AC, so that's why we are taking the value of AC is 0. So the value is increases as shown in figure. So friends, in figure we have the value of VAC, that is voltage across AC. Voltage across AC, now I can show you, that will be the voltage across AC, that will be the increasing in nature. Okay, so from A to C, now we are having, that is from A to C, that is A to C. So this will be the increasing nature. So from A to C we are getting the value that is in increasing nature. So this will be the example for your understanding of the different operation of your three-phase fully controlled rectifier. So basically, as we have drawn the waveform for motoring operation when alpha is equal to 30 degree, and we have drawn the waveform that is for the braking operation when the alpha is equal to 140 degree, and we have understood the detailed understanding of the output voltage of VA at 30 degree, and we have drawn the waveform of VA and IA, that is the voltage across the armature circuit of your separately excited motor and the current in which the armature circuit for your alpha is equal to 30 degree for your motoring operation. Okay, and we have drawn the braking operation, that is alpha is equal to 140 degree. We have drawn the output waveform of VA and IA. So VA is the voltage waveform, I is the current waveform. Okay, so this is in concern with your three-phase fully controlled rectifier fed drive. So now we are moving towards very important concept, that is the finding out the value of your VA by means of the derivation. So for the sake of understanding of derivation, now we can take the, that is VAB is a reference voltage. VAB is a reference voltage means we are taking the voltage across the AB phase supply. So friends, as we know that it is a sinusoidal waveform, so we have the fundamental formula of the sinusoidal waveform, that is VAB is equal to Vm sine omega t. Vm sine omega t means what? It will be the input sinusoidal waveform that will be given to your three-phase supply. But for your sake of understanding, we are considering only one phase. Okay, that is VAB. So we are taking this waveform value is okay. The waveform this value, this is called as Vm sine omega t because it will be with respect to omega t. Okay, so this will be the reference thing. This is will be the equation number first. Now we are taking the value of alpha because we want to take the value of alpha, that is a firing angle. So firing angle value is omega t means with respect to that particular period, that is omega t minus pi by 3 means alpha is equal to omega t, pi value is 180 by 3. So it will be alpha is equal to, that is 60 degree means alpha is equal to omega t minus 60 degree. So this will be the actual phase sequence of your operation, and this will be the treated as an equation number 2. Okay, so what do you mean by the Vm in concern with that equation? So Vm is the peak of line voltage, so this will be the value of Vm, that is peak of line voltage. Okay, so this will be the peak of line voltage, and as we know that these devices are basically in operation in a continuous conduction state. Okay, so the current will be flowing into that particular waveform is in continuous conduction state that we had already drawn. So this will be the current waveform, and this current waveform I can show with the help of yellow color. So this will be the in a continuous conduction state of your current for your braking operation as well as for your motoring operation So this will be the current in a continuous conduction state. Okay, so we can derive the equation. So for the derivation of your equation, we can get the motor terminal voltage cycle from alpha plus pi by 3 plus alpha plus 2 pi by 3, because this will be the conduction angle, that is alpha plus pi by 3 to alpha plus 2 pi by 3. Now we want to get the value of output voltage, that is VA is equal to 3 by pi. Why we are taking the 3 by pi? Because this is a three-phase waveform, and now we are taking the integration of this term. So in that particular integration of term, we are taking the lower limit just as the alpha plus pi by 3, and the upper limit is alpha plus 2 pi by 3, and this will be the input sinusoidal waveform, that is Vm sine omega t d omega t. While we are calculating the value of these all terms, we are using a simple term, that is we are substituting the value of lower limit and upper limit into that equation. So we are getting the simple terminology of the different integration value. We are getting directly the output, that is Va is equal to 3 by pi Vm that we are taking the outside, this is called as Vm, and the integration of your sine omega t d omega t. Now we are substituting the value of omega t d omega t, that is the limit pi, basically alpha plus pi by 3 and alpha plus 2 pi by 3. So we are getting the basically integration value, that is cos alpha. So this will be the output equation of your three-phase fully controlled rectifier. And what should be the output equation of your three-phase fully controlled rectifier? So that will be the output equation, which is called as Va is equal to 3 by pi Vm, that will be the cos alpha. Okay, so this will be the treated as an equation number 3 of your operation. Okay, so from equation number, these are the basic equation of your DC motor, that is DC separately excited motor. So from the basic equation of that particular motor, what do you mean by T? T is called as torque, K is called as motor constant, the IA is called as the current in the armature circuit. So we have the fundamental equation, that is T is equal to K into IA. Okay, this will be the equation the basic number. Then the second equation, that will be the very basic equation, that is equation number first, that is a generated EMF means is equal to K is the motor constant, omega am is the angular velocity. Okay, so this will be the A is the generated EMF, K is the motor constant, and omega m is called as the angular velocity. Okay, then the third term is V is equal to E plus IRA. So what do you mean by V? V is the voltage. Okay, E is the generated voltage, I is called as armature current, and Ra is called as armature resistance. So these are the very basic equations of your DC motor. So friends, now we are using this equation, that is equation number the equation of your torque, the equation of your EMF, and the equation of your voltage. We can get the relationship between the torque and speed. We are getting the relationship between torque and speed because we are substituting the value of this basic equation into that equation. We are getting the value of the torque and speed relationship. So from equation, friends, we are getting the fundamental thing. So this will be the output equation of your three-phase fully controlled rectifier. This is called as VA is equal to, I can show you here, that is VA is equal to 3 by pi Vm cos phi. Now I can substitute the value of T is equal to K into Ia, E is equal to K omega m, V is equal to E plus IRA. Then we are getting the relationship between this torque and speed. So this torque and speed, if you want to get the value of speed, so what will be the equation? E divided by K. So what will be the value of E? Now we are getting the value of E is what? V minus IRA divided by K. Okay, so this will be the divided by K. So if you want to know the value of torque and speed, then we have to substitute this value of Ia. That is, Ia value is what? That will be the T by K. Now we have to substitute this value, that is V minus, that is T by, that will be the Kk. We are considered as K square. Okay, so this will be the value of VA. Okay, VA minus IRA. Now we have to substitute this value of VA into that equation, that is 3 by pi Vm cos phi into that equation. So we are getting the relationship, or we are getting the equation. What is that particular equation? That is omega m is equal to, now we have to substitute the value 3 into Vm, okay, by pi, that is K, because this will be the K terms, that is K into cos alpha minus Ra divided by K square into T. So from that equation we are getting the relationship between the torque and speed, and this will be the showing by the torque speed characteristics of your three-phase fully controlled rectifier. So as we know that, friends, this will be the torque and speed current representation of your three-phase fully controlled rectifier will be operated in a four quadrant of operations, that is in concern with the that particular four quadrant of operation, that will be operated in first and fourth quadrant. This will be the first quadrant, friends, and this will be the fourth quadrant. The first quadrant of operation, that is output waveform, that is VA, regarding the firing angle alpha, we have to draw the first waveform. Okay, because for your understanding of the continuous conduction, we are getting the speed torque curve. So this will be the speed torque curve that we are getting from the fundamental equation, that is the relationship of that is torque and speed. So we have getting the torque speed relationship in a continuous conduction, while we are basically ignoring the condition of the discontinuous conduction. So basically the three-phase fully controlled rectifier will be operated in first and fourth quadrant of operation. So the first quadrant of operation is called as the forward motoring, and fourth quadrant of operation is called as reverse braking. Okay, so this will be the forward motoring and this will be the reverse braking. So the firing angle for that particular thing is now we are considered, this will be the waveform of your firing angle. I can erase all these things. Now you can get the fundamental thing. This will be firing angle alpha. So we have getting V versus alpha curve, which will be getting same nature of curve. Same nature of curve means this will be the operation in first quadrant and this will be the operation in fourth quadrant. Okay, so this is in concern with the three-phase fully controlled rectifier. This will be the output waveform 2 Vm by pi This will be the minus 2 Vm by pi for your motoring operation and braking operation, because we have drawn the detailed waveform for your motoring operation, that is alpha is equal to 30 degree, and we have drawn the detail operation, that is alpha is equal to 140 degree earlier. Okay, so friend, this will be the representation of Va, output voltage, versus firing angle alpha. And friends, this will be the torque speed characteristics. So friends, this will be the torque speed characteristics, this will be the speed, this will be the torque. So this will be the torque, this will be the speed. Okay, so friend, this will be the separately excited motor. So this will be the value of the alpha 0. Now we are consider this will be the 30 degree, this will be the alpha is equal to 60 degree, this will be the alpha is equal to 90 degree, alpha is equal to 120, 140, whatever it will be. Whenever we are using the value of the firing angle is increasing, the motor will be tends to, because this will be the quadrant number first. Friends, you can understand this will be the quadrant number first, that will be the quadrant number first, and this will be the quadrant number fourth. And what do I mean by the quadrant number fourth? Quadrant number fourth is reverse braking, and quadrant number first is obviously motoring operation. This is called as a forward motoring operation. So friends, while we are increasing the value, then obviously the motor will move from motoring state to the braking state. Means while we are increasing the value of alpha, that is firing angle, while we are increasing the value of the alpha, that is firing angle, the motor will be changing its operation, that is from your motoring to braking. So that will be the representation of your torque speed characteristics of your DC separately excited motor by using three-phase fully controlled rectifier. So friends, this is the explanation in concern with the three-phase fully controlled rectifier. Now we are moving towards the next type of converter, and that type of converter is called as three-phase half control rectifier. So what will be the difference in between three-phase full control drives and three-phase half control drives? So friends, as shown in figure, in three-phase half control drives, again we are using the three-phase supply. This will be the three-phase supply, this will be the supply A, supply B, and supply C. So we are using in three-phase half controlled rectifier, we are using 3 thyristor, that will be the thyristor number 1, thyristor number 2, and thyristor number 3. But instead of 6 number of thyristor in concern with the 3-phase fully controlled rectifier, now we are using only 3 diodes in your upper leg. Basically we are using the diodes in a lower leg. Okay, so this will be the diode number 1, diode number 2, and diode number 3 for your lower leg, and 3 thyristor, that is T1, T2, and T3 for your upper leg. Okay, so instead of 6 thyristor, we are using 3 thyristor and 3 diode in concern with the 3-phase half control drive. And 3-phase half control drive will be operated in only first quadrant, because we are using only 3 number of thyristor. So this will be the quadrant of operation of your 3-phase half control drive. That will be the only first quadrant of operation, which is called as the forward motoring. So friends, as shown in figure, this will be the representation of your motor, and this will be the motor which is called as separately excited. So this will be the armature circuit of your motor, and this will be the your separately filled excitation of your motor. So the output voltage across your motor is Va. So for your sake of understanding, we can replace this motor armature by its equivalent parameters, that is R, L, and E. So obviously this will be the also representation of your separately excited motor, in which we are using the various terms, that is RA, LA, and E, that is excitation voltage. The current flowing through that particular circuit, which is called as IA, that is called as armature current, and the voltage across that particular motor terminal voltage, this will be treated as an VA. So friends, for understanding of your 3-phase half control drive, now we can understand what will be the conduction sequence. So for the understanding of the conduction sequence. Now we are giving the supply, that is A, B, C, that is three-phase supply. So now we can understand the sequence of operations. So for the sake of the first sequence of operation, first T1 is conducting. This will be the flowing through the current IA. Then that the current will be the flowing through the armature of your DC motor. So in armature, maybe resistance, maybe inductance, maybe separately excitation. From that we are completing path through the diode D2. So this is for your first operation, in which we are using or the conduction of, first of all we can taking, that is the first phase, that is going to the thyristor number first to the armature current, that is IA. Then the armature circuit of your motor, this will be the value of RA, this will be the LA, and separately excitation E. Then it will be moving through the diode number 2, that is called as D2, and from that it will be complete its path. So this will be the operation for your first leg. We call it as the first leg, in which we are conducting the T1 and D2. Okay, T1 and D2 for AB voltage. Okay, then for your second operation we can consider, this will be for your second conduction, this will be the phase now A, B and C. So this will be this for your second phase, that will be the thyristor number second. Then the armature current IA from motor, that is armature of your motor. Then it will be moving to T2 and complete its path from D3, that is the diode D3. Okay, so this will be the second thing. Okay, so this will be the conduction for your that is the thyristor T2 and the diode D3. We are getting the output voltage across VBC. Similarly, while we are taking the operation number third phase, that will be the for your third phase. Now we can understand, this is for phase A, phase B and phase C. For your phase 3, so this will be the conduction of thyristor number third to the armature current IA. Again it will be moving from the armature circuit. Okay, from that particular armature circuit, now it will be moving to basically so basically this will be the operation across the, when we are using the conduction of T3 and D1, that will be operation give you VAC for your three phase half control drive. Okay, so this will be the operation of your three phase half control drive. So from that operation, friends, we are getting the this whole operation under continuous conduction. So we are getting the output equation of your VA across your separately excited motor. That the output equation will be getting, that is 3 Vm by 2 pi in bracket 1 plus cos alpha. This will be the treated as an equation number 5, and we are getting the same equation from the waveforms of your three phase half control rectifier. So from the basic equations, that is the basic equations are in concern with your torque equation, your generated EMF equation, and the voltage equation, that is torque is equal to K into IA, where K is the constant, I is the armature current, K is the constant, the value of the omega m is the angular velocity, the value of E is called a generated voltage, the value of IA is the armature current, the value of RA is the armature resistance. So from that particular fundamental equation, friends, now we can substitute. What we can substitute? We can getting the torque and speed relationship of your three phase half control drive. So what will be the three phase half control drive's torque and speed relationship? If you want to get the value of speed, that is omega m is equal to E by K. So what should be the value of E? The value of E is what? VA minus IARA. Okay, so if you want to get the value of the torque and speed, then we want to substitute the value of IA is equal to T by K. So friends, now we can substitute these all values into that equation. So what will be the value? That is omega m. Now we can get omega m is equal to E is equal to VA minus IARA divided by K. Now we can substitute the value of IA, that is T by K, into that equation. So we are getting the equation omega m is equal to VA minus or VA by K minus, that is T into RA divided by K into K square. So we are getting this term is as it is. Now we want to substitute the value of VA into that equation. So what should be the value of VA? So that VA is equal to what? 3Vm by 2 pi in bracket 1 plus cos alpha. It is 3Vm by pi. Okay, that is 3Vm by 2 pi. So this will be the 3Vm by 2 pi as it is. This will be the K, which will be substituting here, and this will be the 1 plus cos alpha. So we are getting from these basic equations, now we are substituting this equation into that particular thing. We are getting the torque speed relationship of your three phase half control rectifier. Okay, so this will be the torque and speed relationship of your three phase half control rectifier, and this will be the showing look like that, because as we know that this will be the V versus alpha, means this will be the output voltage versus alpha firing angle. So as we know that this will be the three phase half control drive, so it will be operated only in first quadrant. Okay, so this first quadrant is called as forward motoring operation, and we are getting the output waveform of three phase fully controlled rectifier, because we are using, this will be the, suppose one waveform for phase 1, we are using another waveform for phase 2. Suppose we have drawn another waveform for your phase 3. So these are the three-way output waveform, and we are getting the output from that particular, this will be the treated as the output of your half control rectifier. So this will be the period of your diode period, this will be the conduction of your thyristor period. Okay, so this will be the thyristor period, this will be the diode period. So it will be operating only in first quadrant. So that will be the operated in only first quadrant. So it will be give you a forward motoring mode. Okay, and while we are increasing the value of the alpha with respect to your VA, the value of VA, that will be moving into only a first quadrant of operation, and that the first quadrant of operation is called as, again I can write, that will be the forward motoring mode. Okay, friend. So in this way we have detailedly study the different types of the three phase as well as the full control and half control DC drives. So friends, we can understand what are the different advantages of the three-phase drive. So friends, we are using the three-phase drive in the industry in a day-to-day life, because of that the three-phase drives are used for the high capacity of your motors are driven with the help of that particular drive. So that will be the first advantage. Then the second advantage is what the three-phase drive does not heat the motors, because the ripple contents or the ripple frequencies are very high. So due to that it doesn't heat the motors. So that will be the second advantage. Then the third advantage of your three-phase drive is that the chances of discontinuous armature current is reduced by means of the three-phase circuit, because in single-phase circuit the chances of discontinuous current will be more, but in concern with the three-phase supply we are giving simultaneously three-phase supply. So due to that the chances of the discontinuous of the armature current will be reduced, obviously. Then the third, that is due to 1, 2 and 3 point, obviously the motor performance is improved in terms of the regulation. So what do you mean by the regulation? Basically in concern with drive we are moving towards the rotational motion, so we want to calculate the value of the speed regulation of your drive. So that will give you definitely the better speed regulation of your electrical drive. So obviously the torque speed characteristics is improved by the means of the three-phase converter circuit. So the three-phase drive will give you the overall better dynamic response of your drive. So that's why in most of the time in the industry we are preferring a three-phase drive for a higher power rating of your applications. So friends, after that there are different limitations of your three-phase drive. So the first limitation of your three-phase drive is called the control circuit is quietly complex because we are using the more number of thyristor in concern with the three-phase fully controlled rectifier circuit. So the control circuit is quietly complex, and obviously the circuit is very costly and bulky. So this will be the limitations of your three-phase control rectifier. So after that, we can understand what are the different applications or where the three-phase controlled rectifiers are used. So basically the three-phase fully controlled rectifier or the three-phase half controlled rectifier are preferred in the high power DC drives. The second application that we are using for the traction purpose, we are using the three-phase rectifier converter circuit. We are using high power conveyor belts for different types of three-phase converter circuit, and we are using for the high power belt drives three-phase converter circuit. So friends, in this way we have detailedly studied about the three-phase converter circuit. This is called as a half converter, full converter. There are different advantages of such converter, there are different limitations of such converter, and the different applications of such converter. So thank you very much.